So let's start our unit on regression. So first I'll just do a recap and talk about simple linear regression, which is just one feature, multiple linear regression, which is many features, how to evaluate regression models, and we'll do a case study. And then we'll talk about outliers and the concept of leverage. Okay, let's start with a recap. Regression is for predicting real valued outcomes. Things like how many customers will arrive at our website next week, how many TVs are we going to sell next year, and can we predict someone's income from their click-through information. Okay, so here's our training data, the features here, and the labels, which are real valued. In this case, it's income. And then we also have the predictions, f of x, over here on the right. Now, just looking at these two columns, we have to figure out how to evaluate the closeness of the truth y to what we predicted, which is f of x. Now, here's what I propose, which is y minus f of x. And as we know, that is not a great idea, because why didn't I choose that one? Yeah, if I choose either this one or that one, it would be bad, because I'm looking at errors in only one direction, and I want to penalize mistakes in either direction. So I could try to use this penalty here, which makes sure we count deviations in either direction. But that's not actually what we're going to use. We're going to use the least square, the squared error here. It's just easier computationally and analytically because it's differentiable. But you should think of this as just capturing errors in both directions, just like the absolute value that I had on the previous slide. So same deal, penalize how far y is from f in either direction. So here's a picture of it. Here we would want to use f of x minus y. And then here is a case where we'd want to use y minus f. And so we could just use the absolute value to capture both of those things, but we're not going to. We're actually going to square it, get the squared error. Now, the sum of squares errors, this is, if we add all these errors up, it's called the sum of squares error. And we'll get back to that in a minute, and that is right here. But I want you to remember that this is a fundamental quantity in regression. And what I want to do now is talk about what the model f might look like. We're going to choose f so that it's a good model, meaning that it minimizes this sum of squares error. So let's talk about simple linear regression. In simple linear regression, we have only one feature. So maybe we're predicting, say, income based on a single feature, which is maybe the number of business week clicks the person makes. Okay, so now we have to figure out what our function f is going to look like. So here I put on a very simple function f. It just gives everyone a baseline of $100,000 just for existing. And then it estimates that for each click they make on the Business Week website, they're $5,000 richer. So this is kind of a silly model since it predicts that anyone who spends all of their time on Business Week is a gazillionaire, but hey, it's just an example. Okay, but for our function that estimates y from x, we're going to choose a model of this form. So a baseline plus the multiplier for however many Business Week clicks we have, called B1, times the number of clicks, which is x1. So there's the formula again. Before we start doing this, all we have is data. We don't know this $100,000 and we don't know the $5,000. I just made those up. We have to estimate them by using data. Now remember, we want the sum of squares error to be small. So what we're going to do is choose the B0 and the B1 to minimize the total error on the training set. And that is the procedure of simple linear regression, least squares regression. So let's pretend I did this. And as it turned out, actually the model I had before wasn't so good. When I fit it to the data, I got this model instead. And this new model fits pretty well on the data that I have in my training set. But how well does it perform out of sample? I didn't tell you, but I actually left part of the data out for evaluation. And there it is. So let's take a look at the errors. And they're here. Not too bad. Looks like we did a pretty good job. So that is the procedure of simple linear regression, least squares regression for a single feature. You don't need to solve the minimization problem yourself to find B0 and B1. The machine learning algorithm will do it for you. It's all under the hood.